Continuing our discussion of analytical geometry and trigonometry, now I want to look at trigonometry. And firstly, we defined the simple functions, sine, cosine, etc., from a right triangle where r is the hypotenuse, x the adjacent, and y opposite relative to the angle theta. So sine theta is opposite over hypotenuse, y over r, cosine theta is adjacent over hypotenuse, etc. For a more general triangle with sides A, B, and C, and interior angles A, B, and C opposite to those sides, we have the law of sines, which is A over sine A is equal to B over sine B is equal to C over sine C. In other words, the length of this side A divided by the sine of the angle which is opposite to us is equal to the length of B divided by the sine of its opposite angle, etc. And another convenient law or equation is the law of cosines, which can be written in terms of the three different angles as shown here. A squared is equal to B squared plus C squared minus 2BC cosine A, and similar equations for the other two angles. The sum of the interior angles in a triangle is equal to 180 degrees. And more general, for polygons of arbitrary number of sides, the sum of the interior angles is equal to the number of sides, or the number of angles, minus 2, multiplied by 180 degrees. And for regular polygons, such as sketched here, where all the angles are equal and all the lengths of the sides are equal, the magnitude of the interior angles is number of sides minus 2 times 180 divided by the number of sides or angles, n. Let's do an example on that. And the question is, an observer surveys a building and observes that the vertical angle to its top is 40 degrees. He then walks 50 meters farther away and observes the vertical angle to be now 30 degrees. The height of the building is most nearly which of these alternatives? So here's a sketch. So we have the building, and here is the first observation point, which I'll label A. And he observes that the angle to the top of the building is 40 degrees. Then he walks 50 meters away, so this distance is 50 meters, to the point B, where he observes that the angle is 30 degrees. And the question is, how high is the building? In other words, the height CD in those triangles. So the steps involved here, first we want to find this angle theta by looking at the triangle ADC, the right angle triangle. So the sum of the angles in that triangle is 180 degrees. So 40 degrees plus 90 degrees plus theta is 180. Therefore, theta is 50 degrees. Next, we want to find the angle phi by observing the triangle BDC. And again, the sum of the angles in that triangle is equal to 180 degrees. Therefore, 30 plus the right angle plus phi plus theta is 180. And we already know theta, so therefore the angle phi is 10 degrees. Next, we'll use the law of sines on the triangle ABC to find the length of the inclined side AC. So we have BA, this length, divided by sine phi is equal to AC, this length, divided by sine of 30 degrees. So rearranging, we have AC is equal to 50 sine 30 degrees divided by sine 10 degrees is equal to 144 meters. And the final step is to look at the triangle ADC to find the height of the building. And there we see that DC is equal to AC sine 40 degrees. In other words, 144 sine 40, which is 92.6 meters. So the answer is C. There are a great number of trigonometric identities given in the handbook, and I've listed some of them here, and it's not clear which or any of these will be useful, but a few of them might be, for example, sine squared theta plus cosine squared theta is equal to 1, and all of the others, of course, you can look up in the handbook as needed for any particular problem. Next, the handbook discusses mensuration or measurement of areas of various shapes, for example, parabola, ellipse, circular segment, etc. And an example is given over here. The area of a parabola, of half a parabola of height h and width b, is given by this formula. A is equal to 2bh over 3, where a is the area and p is the perimeter. And it also gives volumes if this is a three-dimensional object. So this is the area of the parabola above the curve there, above the concave curve, and above a convex curve, the corresponding equation is A is equal to BH over 3. And similar equations are given for all of the shapes which are listed over on the left-hand side here. The shaded circular segment shown is bounded by the chord of a circle of radius r equals 2 meters, and it has an arc length s of 1 meter. Its area is most nearly which of these four answers? So here is our definition sketch, which is similar to the one in the handbook. We have a radius r, a height of the segment d, and an arc length s, and an interior angle phi. So the equations are phi, the interior angle, is equal to s over r, which is 2 cosine arc of r minus d over r. So in this case we have phi is s over r, s is given as 1 meter, r is 2 meters, so the angle phi is 0.5. And remember, of course, that when we calculate it like this, the units of the angle are in radians. The equation for the area is r squared phi minus sine phi over 2, which in this case is equal to r is 2, 0.5 minus sine phi, and I've converted phi here to degrees. You don't need to, you can leave it in radians, all divided by 2. So calculating out, we get 0.0396 square meters, so the closest answer is D. And this concludes our discussion of the mensuration of areas.